Today we'll be talking about the sort of second lecture on these approximation algorithms for stochastic optimization. The previous lecture, you saw a basic introduction to approximations, and it was a bit quick, but hopefully you've got a sense of what the ideas are and how to use linear programming and various other basic techniques, and some of the jargon as well, because there is some jargon, and I do tend to use the jargon. So if you feel confused, do ask. Today, I'm going to talk about one of the sort of most basic stochastic models, and it somehow hopefully should bring to life the issues that are there underlying this. And then in the next couple of lectures, we'll go into more detail and more sophisticated arguments and things like this. Good. So today's lecture is essentially this topic of multi-stage stochastic optimization, and you'll see what multi-stage means with recourse. And all these terms should become clear to you. We'll talk about a couple of problems, and we'll again use LPs and rounding to solve these problems. Yeah, good. Okay. So this model perhaps is best explained by the paper that introduced this model, or in fact, the introduction to the paper that introduced this model. So this paper is by George Danzig from '54 or something like this. And you can read it out here. So basically, it says that the models are divided into 2 or more stages. And only the first stage are the ones that are needed to be determined. Once you know the first stage, the second stage and others cannot be determined in advance since they depend on earlier stages. So there's a sequence of adaptive decisions that need to be made. In this case, actually, there is only one adaptive decision that needs to be made on the second stage. So let's just look at 2 stages. In the first stage, you make some decisions, but you make them in anticipation of the second stage. In the second stage, you make decisions that fix the problems that actually arise. Okay. It says, it is important to note that the set of activities are assumed to be complete in some sense, that whatever the choice of activities in earlier stages, there is a possible choice of activities in later stages. It is not possible to get into a position where the programming problem admits no solution. And if you read this, it explicitly lays out a very concrete and precise model. And maybe let me give this model in sort of in bite-sized chunks. We all being kids of the Twitter generation. I'm counting myself as a kid of the Twitter generation. I don't know why, but today we know some demand distribution, pi. Tomorrow we'll get to know the real demands, and these real demands are actually drawn from pi. Okay. Today things are cheaper, and in today's lecture things will be cheaper explicitly, but often there's an implicit cost. We'll deal with that when we come to it. Tomorrow prices go up. Okay, so you want to buy it today rather than tomorrow, but of course today you don't know the actual demand that you'll have to face. So there's this natural tension between the two things. Okay, with recourse just means you can't mess up. If today you actually made some decisions and tomorrow you need to fix things, well, you can always fix things so that the solution will always be feasible. Okay. Now, one thing to note is that, well, if you're trying to solve a problem, then this problem, if lambda were 1, you should just wait until tomorrow. Then you'll know the actual input. And then you can solve that problem. So then it's a one-stage problem. And this one-stage problem is just some optimization problem. So I'm just saying, here is an optimization problem where the demand is presented in 2 stages. On the first stage, you only know pi. In the second stage, you know everything. How would you deal with such a situation? And this is the real sort of crux of today's lecture. So today's lecture is going to be, let's look at an example. It's a sort of very concrete example. Vertex, it's a problem called vertex cover, which you saw yesterday as basically hitting set with sets of size 2. Okay. So really, every set is an edge of the graph. So I have a graph. And now nodes have costs, let's say. A vertex cover is just a collection of vertices such that every edge in this collection has one endpoint, at least one endpoint in this vertex cover. Okay, and you want to pick the vertex cover at the least cost. And as we discussed briefly last time, and maybe I'll revise it this time, that we know, okay, for this we know like a 2 approximation. And this is the best we know right now. 1.99 would be a big deal. The stochastic question is the following. I'll give you this graph. But the actual edges you need to cover are not known today. They'll appear tomorrow. Okay. Say there'll be a random sample of 10% of the edges. Let's say, just for simplicity, every edge will appear independently with probability 0.1. Or there might be some more sophisticated distribution of these things. But the node costs are changed. Tomorrow they're going to be higher in general. Which vertices should you choose today and which vertices should you choose tomorrow? And in fact, when you first start thinking about it, you'll ask even the single question, if there's a single edge, and you know the probability with which it will appear tomorrow, should you buy today or should you buy tomorrow? And you can see this is a simple calculation, but once it becomes a graph with more combinatorial structure, it's not completely clear how to approach this. Okay, good. What do you want to do? You want to minimize the expected total cost incurred over 2 days. I'm making a choice out here. There are many different objective functions you could have chosen. I chose this one. It's clean, conceptually simple, and we can move on to other things as needed. Actually, sort of like the issues like the variance or the probability of exceeding some budget is also a very interesting question. And in fact, those are questions which are currently hard. We don't understand them very well. But for today, it's the expected total cost over the 2 days. Okay. So that's the problem that we want to solve. As always, as we talked about the other day, yesterday, we want efficient algorithms. Algorithms, for us, efficient means algorithms that run in polynomial time. We would like to give provable guarantees on the performance. So on every instance, it should do well. And our framework is that of approximation algorithms. We compare our expected performance to the expected performance of the optimal algorithm. Moreover, ideally, we would like our algorithms to work for general distributions, but maybe sometimes life is tough, and then we work on sort of nice distributions, like distributions where every edge appears with probability 10% independently. But in general, I would like as general a distribution as possible. Okay, good. So today's roadmap, I'm going to give a couple of problems, and I'm going to illustrate the idea on this. I'm going to talk about a general idea called sample average approximations, and maybe tell you the generic theorem. Then we'll see how far we can go. With probably 1 hour, I don't expect to be able to cover all the stuff that I have in mind, but at least I can give you a sense of what's happening. And as always, I won't dive too much into all the proofs, but you should play around with the proofs, and if you have questions, I'm happy to answer more of them as they come up. Okay, so our problem again, stochastic vertex cover, 2 stages. So here's the thing. This is a general statement, the probability distribution pi. So let's just talk about the probability distribution pi a little bit. So each possible outcome tomorrow. So tomorrow, what can happen is, it can be the case that every edge appears with probability 10% independently, or it might be the case that, there is some, this set will, these 3 possibilities are the only possibilities there are, with probability, 10%, 60%, and 30%. Or it could be some more complicated object. It's a probability distribution, right? And the probability distribution gives a distribution over sets. Okay, good. So how, this probability distribution pi. A vertex costs CV on Monday and some cost on Tuesday, depending on what scenario appears. This could be a very complicated object. For every possible outcome, you say, oh, if this edge appears and this edge appears and this edge appears, then the cost of this vertex is 72. Things like this. It could be very complicated. Right now, the model is very general right now. Okay. What do you want to do? You want to pick a set of guys on Monday. And then once you actually know the actual edges, you can fix the problem. You can pick some other set of vertices on Tuesday such that Monday plus Tuesday covers the actual edges that have appeared. And you want to minimize the cost of Monday plus the expected cost of Tuesday. Okay. So formally, I've given you the model with one caveat. I haven't told you how the input is represented. How is this distribution pi given to me? So for simplicity, for the first half of today's lecture, let's consider the explicit scenario model. I give you this list. I'll give you a long list. I'll say, hey guys, this is going to happen 10%, this 60%, whatever. And let's say that this list is of size capital N. Now, of course, you might say this capital N could be of size 2 to the k, right? Or 2 to the number of edges. So I should be worried, how am I even going to read this list in reasonable time? But let's not worry about that for the moment. We'll come back to this question. This is a very important question. We'll come back to it. Okay? But right now, I give you this explicit list, and I say, okay, solve this. Think of this list as having, 1,000, 10,000 possible scenarios. Okay. Is the problem clear? Okay. Good. So I'm going to talk about the explicit scenario model. Just to give you a sense of what could be there. There could be a black box model where you give me a box and you say this is a sampling. This is a box with a sampling axis. You push a button and a random scenario appears. Or there could be independent decisions, or they could be even more specialized. It could be a parametric distribution of some kind. I'm going to talk about explicit scenarios for the time being. You'll see that we'll come back to this and we'll talk about black box. Okay, good. So I want to solve two-stage vertex cover. And in order to solve this, you can go back and you can ask the question, how would you solve vertex cover in the one stage? And this is the first thing you would ask normally. I want to solve a two-stage problem. It's a generalization of a one-stage problem. I should understand what the one-stage problem solution is. And this, I'm writing down this solution that we laid out last time. We first write down the integer linear program. Says minimize the total cost subject to every edge being hit and every variable being chosen either to 0 or 1. XV is 1 means the vertex is chosen, XV is 0 means the vertex is not chosen. Right? And this is really the problem that we want to solve. The standard vertex cover, no stochastic, right? Okay. How would we solve this? We had the relax and round paradigm. We relax it. We say, well, let's say XVs are between 1 and 0. Let's even say. This is the relaxation. So I get an LP whose cost is at most the IP because I'm minimizing. And then I say, hey, let me pick a hitting set, which is equal to all the vertices I such that xi is at least 1/2. So I solved the optimal, I got the optimal solution. Let's say the optimal solution is X star. So solve LP. And now I say, well, pick all the vertices whose value is at least 1/2. This is going to be a feasible solution. Why? Because for every edge, one of the two endpoints must be at least 1/2. That's it, right? So fact, edge is feasible. Vertex cover. And then the second fact is that the sum of costs is at most 2 times this is just following from the fact that every vertex in H was at least 1/2. And so for every vertex in H, the contribution to the left is 1, and the contribution to the right is 2 times at least 1/2. And that's it. Right? Good. So this is the LP value, 2 times the LP value, which is 2 times the IP value. And so you're done. So this was our approximation last time for vertex cover. Okay. And now you'll see, we're pretty much done for the two-stage problem. And it's almost an embarrassment to write down this this second stage, this idea, but it's good to start off easy, right? So I'm actually going to have one variable for every, for the first stage, and one variable for every possible outcome in the second stage. So remember, this LP is huge, and we are coming back to this question. What if the list of scenarios is very large, right? But right now I said list of scenarios is bounded. So this LP has one variable per vertex and per scenario. And it really just explicitly writes down subject to, well, either for every edge UV, either its left endpoint is covered on day 1 or on day 2, or right endpoint is covered on day 1 or on day 2. If this edge appears in scenario K, and scenario K happens. It's just like explicitly writing it down. It's almost like you should just think about the problem and write it down as an IP. And so I'm writing an integer program which captures the stochastic problem. For every edge in every scenario, I'm going to cover it, either on day 1 or on day 2. And I am going to pay, this is exactly the cost of day 1, and this is the expected cost of day 2. Okay, good. Good. So this IP is exactly equal to the problem we want to solve. Stochastic problem. And how do we solve it? Well, relax and round. You relax it. And now there are four objects on every in every constraint, and it wants to be at least 1. So if you choose the vertex, the set V0 to be all the guys who are at least 1/4, and choose Vk to be the guys who are at least 1/4 in the kth scenario, then the claim is that V0 union Vk is a vertex cover for scenario K. Just as simple as that. Okay. And we are increasing the variables by a factor of 4. So we'll get at most a 4 approximation. Yeah, very simple, easy. Good. By the way, this is a sort of an interesting exercise, and this is a slightly subtle exercise, but worth trying. Can you actually get it to approximation? I mean, what you did was the sort of simplest thing. You said, look, this is really just a hitting set problem. In some sense, there are 4 variables on each side. They must have sum up to at least 1. So there's, at least one of them must be a quarter. Can you do slightly better? But there's more structure in here, right? So I'm leaving this as an exercise, and we can discuss this more as we go on. So in fact, this is doable, and you can get a 2 approximation for this problem. Okay. Let me give you another problem where actually now we'll have to do a little more. It's the same idea. So I want to build on this thing. Okay. So what's the problem? Okay. So let's stretch mentally. Okay. So what are we doing? I want to solve a problem called stochastic MST. Okay. I give you a graph. There are sort of there are lengths on the edges, and you want to build a spanning tree. But now you can buy an edge either on Monday or on Tuesday. You know the Monday costs. The Tuesday, you don't know what's going to be the costs. The costs might go up, might go down. So the costs vary, right? But there are scenarios again. In scenario K, there are some costs for every edge on Tuesday. Which edges should you pick on Monday? Which edges should you pick on Tuesday? Right? So you'll buy maybe, you say this edge is going to go up by a huge amount on Tuesday. Maybe I should buy it. This edge should go up by a huge amount. Maybe I should buy it. And then, maybe you'll buy this edge. And then on Tuesday, you'll see the actual costs and you'll buy some more edges. It seems like a very sort of natural problem. One of the motivating problems when these things were actually being studied. Minimize the expected total cost. Okay. So we'll see an approximation algorithm and a hardness result. And in some sense, also illustrate a sort of some cute ideas out here. So I'm going to use relax and round again. This time, here's what I'm going to do. This is a bit of a mouthful, so let me read this out to you. So I'm going to have a variable for every edge. And I'm going to ask for the following LP to be solved. Okay. So what am I paying on Monday? So think of XE as, again, am I buying the edge by edge? If this is equal to 1, buy edge on Monday. And this is saying if scenario K, buy edge on Tuesday. Okay. And now I'm saying the following thing. For pick a set S and look at the complement of S. At least one edge. So sum over all the edges that go from S to S bar. So this is this notion of delta S is the set of edges leaving the set S. Okay. So look at all the edges that leave the set S. At least one of them must be chosen either on Monday or on Tuesday. Okay. And this must be true for every set S because the graph is connected, right? So if the graph is connected, there cannot be a set which is not connected to its complement. So look at every set which is non-empty, whose complement is not empty. So this is a cut in the graph. And look at a scenario. And in that scenario, this cut must be crossed. Okay. Really, you can think of this as a hitting set problem again, where you are hitting all cuts. Here, I'm thinking of the spanning tree of a graph as an object that hits every cut of the graph. In fact, it's the cheapest object that hits the minimum spanning tree, is the cheapest object that hits every cut of the graph. Okay, it's just another hitting set problem. Okay, but now the number of objects, number of sets you're hitting is 2 to the n minus 1. Every possible cut of the graph. Okay, good. That's fine. So I can write a hitting set problem like this, and then I can try to solve it. You know, how to round. You know, I solve it. So I wrote down this IP, which is exactly my problem, stochastic MST. And then I wrote down the linear programming relaxation, which is only cheaper, but now I need to round it. How do I round it? So maybe, you know, the thing that I'll tell you is the perhaps the sort of even more basic question. Once you understand this, you'll see the extension. Forget about the second stages for the time being. This is a relaxation for the MST problem. And I want you to round this thing for me. Okay. There are many ways of rounding it, but good. So there's a question that says, how do we use the LP solver if there are an exponential number of constraints? Excellent, but thank you. So one of the things that good. So there are two answers to this, at least. The first answer is that you can use something called the ellipsoid method, which, or you know, this is a fancy word for, there's another thing called row generation methods, row or column generation methods. Or, you know, sometimes these are also called cutting plane methods. So these are approaches which allow you to solve exponentially many LPs with exponentially many constraints. All you need is a procedure that can figure out a violated constraint. And maybe what I'll do is I'll sort of will put you in touch with pointers about this. Another thing that you could do is you could take this LP and you could rewrite it as a more compact LP. And it's doable in this case, but we can talk about that as well. But for the moment, there are ways, you know, just maybe take it on faith. There are ways to solve this. We just need to round this. Okay. Any other questions? I know that's sort of, it's one of the sort of classic cop-outs of answering questions, right? You just refer somebody to some other result that you haven't talked about, but you know, we only have so much time right now. We can chat more. Okay, good. So now, let's say that we have this solution. It's just, you know, it's a fractional spanning tree. Every edge has some XE, XE prime, things like this. I know that every cut is crossed up to at least one fractionally. I want to solve this integrally. Okay, so here's one way of doing this. Okay, so by the way, this is a hitting set problem, right? And you know an algorithm for hitting set. What do? You scale up all the variables by some factor and you round them. How much do you scale up by? Log of the number of, so you can say you scale up by log of the number of sets. Okay. In this case, the number of sets is like something like 2 to the n. 2 to the n minus 1, but who's counting, right? So every edge will have to be scaled up by n. It's like a terrible algorithm. We shouldn't be using this algorithm. Okay? Let's, this is a bad algorithm. So let's do a better algorithm. Okay. Here's what I'm going to do. I'm going to scale things up by actually much less. So here's what I'll do. I'll sample every edge independently, just with probability xc, right? And remember, I had to do this n times, but what I'm going to do this, I'm going to do this only log n times. Okay. And my claim is that the union is a spanning subgraph with high probability. Okay. So then this is just a general question for you. If I gave you a LP solution like this, and my rounding procedure is every edge is sampled independently with probability xc, and I do this log n times, maybe 10 log n times or something. By the way, whenever I say big O, often I mean big theta. Okay, 10 log n times, let's say. I want to claim that the union is a spanning tree with high probability. Or at least a spanning graph. I might pick cycles and stuff like that. Let's not. How do I show this? So the main idea is that the number of connected components, and here I'll use this structure. See, remember, I had 2 to the n sets, but these 2 to the n sets come from cuts. And these cuts have a lot of nice structure. So here I use the structure that the number of connected components halves every time. So let me do the argument a little bit. Okay. So here's the idea. Initially, I have n components. Look at a component. So it's a vertex, let's say. So all the components are vertices. Look at the edges that leave this vertex. They sum to at least 1, right? Because this is a cut. So the probability that none of these edges chosen is that, which is at most product of e to the negative xc, which is e to the minus because of this constraint. So every vertex, so the probability that V is connected to someone else is at least 1 minus 1 over E. So every vertex has a 63% chance at least of connecting to somebody else. So the expected number of vertices, expected number of components after the first round. So in the first round, every vertex was a singleton. Every component was a singleton. The expected number of vertices after the first round, or the expected number of components after the first round is going to fall by a constant factor. And now look at a component. There's maybe big components form. Maybe these two guys did not form components. But now look at the components. The number of components is going to fall by a constant factor in each round with constant probability. You're making progress. Okay, good. And this is a very simple idea, but the simple ideas get you a lot of the way. And I want you to, get this sort of feeling that you can dive in, you can do this stuff. Good. Okay, and that's the main idea. Okay? And, and once you know how to do this just for a single just the non-stochastic version, you can extend this to the stochastic version. For every edge, add it to the first stage with probability xc, and to the kth scenario of the second stage with probability xk. And repeat this log of mn times, where now I'm using little m as the number of scenarios. Maybe I should use capital N. It doesn't really matter. It's a notational issue. Okay, and the same proof goes through, really. So the expected cost is not much more than the LP cost, which is not much more than the opt cost. And then with high probability, A union BK is the spanning tree of the graph. Okay. By the way, one thing to sort of mention that we've been thinking about. So some of you might know that if you took the complete graph Kn, and suppose you put Xe equals 1 over n minus 1 on all the edges, okay, then it satisfies maybe, let me just go back a couple of slides. So this slide, let's say. So I'm back to just the basic one-stage problem, and I'm imagining the complete graph, and I'm setting Xe equals 1 over n minus 1. Then it satisfies these constraints. Every cut is crossed to an extent of at least 1. Okay. And then what did I say? Basically, I'm saying you'll pick an edge log n many times. You'll sample from this distribution log n many times, and the graph will be connected with high probability. So basically, more or less, this is this is saying the probability that G, the random graph that you're getting, is connected is like 1 minus little of 1 if repeat log n times. But sampling every edge with this probability log n times is kind of like sampling every edge with probability log n over n minus 1. Okay. In fact, I'm cheating C log n, some constant times log n. Right? Now, here's the fact that you might know. If you take the complete graph and you pick every edge with probability really ln n over n plus little o of 1, the graph is very likely to be connected. And if you pick it with probability ln n minus little o of 1, with very high probability, the graph is not going to be connected. This is a fact about random graphs. What this result is doing is it's giving you a cheap version of this. It's saying the graph is very likely to be connected at some constant times log n. But it's actually giving you more. If your graph was deregular, it's showing you that the graph is very likely to be connected at constant times log d. And so this is like a cheap, quick version of the connectivity result. If you want the tight behavior, you'll have to do much more work. But, okay. So there's sort of, you can start to think about other directions. Good. Okay. So the point I wanted to make was, here is an algorithm. I wanted stochastic MST. Which edges should I buy on day 1, day 2? I wrote this IP, relaxed it. The first rounding was terrible, but the second rounding's pretty good. It's log n, log of number of vertices times the number of scenarios. And interestingly enough, this is pretty much the best you can do. So you can actually show, and maybe, I want to get to sort of another part of the talk. So maybe what you can do is you can
Anupam, there's a question in the chat.
Please. Oh, let me check. So, and absolutely, Victor. So it is indeed the case that I might be buying. So almost definitely, I should never buy cycles in the first round. So what I should do is, once this algorithm is giving me something which might have cycles in A or cycles in BK, or actually cycles in A union BK, right? So once you have the solution, you should throw away all cycles from A. And then you should augment each BK and make sure that you never add a cycle. So you can be greedily, you can reduce the size of the sets. That will only improve your cost. Perfect. Good. So there's one last thing that I will mention is that you can actually show that if you can solve stochastic MST, you can approximate stochastic MST better than some factor C, then you can get a hitting set algorithm with the same factor. Okay. And let me give you a very impressionistic view of what's happening. I want to solve hitting set. Remember what was hitting set? There are sets S1 through Sm and elements E1 through En. And I want to pick the smallest set of elements which hit all sets, right? So here's the thing. I'm going to create a stochastic instance where on the first day, this is all you can buy. You can't buy any of the edges downstairs. And on the second day, for a set S, so I'm going to pick one of the sets at random. I'm going to connect it to all its elements. And I'm going to connect up the rest of the world separately. So there's this portion. Let me just use a different color. So there is this portion which is connected to each other. So this set contained these three elements. And the rest of the world is connected to the root. Okay. So here's the deal. What you should be doing is you should buy a hitting set on day one. If you buy a hitting set on day one, then on day two, you are guaranteed that you will have bought. So maybe I'll use a red edge. So let's say that this was a hitting set for my instance. Okay. So on day two, I am worried that the edges that I've bought on day one will not connect up the graph. Okay. But if this were a hitting set, then I would have bought this edge.
So Anupam,
please.
Sorry, one question. So when you're saying that you're given some edges, this means that they're like have cost zero either in the first stage or in the corresponding second stage.
So okay, let me say that a little more carefully. So on day one, the only edges that you can buy are these edges, and they all cost 1. All the other edges are not present, so they cost infinity, let's say. On day two, all edges are either cost 0 or infinity. These edges have cost essentially 0. 1 over mn is like 0. So these edges have cost 0. And these edges have cost 0. And all other edges have cost infinity. Good. So actually, thank you for stopping me, Jose.
Thanks.
So here's the deal. On the second day, I can connect up, I can buy all the 0 cost edges, right? They're cheap. But the only edges I can't buy are the edges crossing between this island out here, between this island out here and the rest of the world. So what's the deal? I should have bought a bridge on day one, right? I should have bought a bridge connecting the elements in S1 to the root. So I should buy a bridge connecting this island to the root, but this is just one set, and there are many such sets that are possible. So I should buy a bridge connecting every set to the root. That's a hitting set. So on day one, the best thing to do is to buy a hitting set. Does that help, Jose? Good.
Perfect, thanks.
Yeah, I was going too fast. I realized I only have like 10 minutes left, but that's okay. I don't have to, there's no sort of agenda that I have to give you all these things. Now, for the rest of the thing, let me just give you again a sense of what's happening out here. Okay, so this shows a reduction. This shows that if you could solve stochastic MST better than hitting set, then log n, then you can do hitting set better than log n. So you can't do, assuming p not equals np, log is the best you can do. And we got a log approximation. Okay, good. Okay, so let's take stock of what we've seen in detail. We saw a 4 approximation for vertex cover, and 2 approximation we are claiming is an exercise. It's a it's a little start exercise, but it's an exercise. Better than 2 approximation will refute the unique games conjecture. So we have the right answer. For stochastic MST, we have like a logarithmic approximation for explicit scenarios. Better than log n would mean p equals np, so that's not possible. I don't believe that's possible, but we'll see. So we seem to have the right answers for these 2 problems. Okay? At least up to constants for this one. And this depends, yeah. Good. And both of them use this relax and round framework. So maybe, the next thing that I want to sort of talk about. So one of the things with relax and round is it's very useful. There are 2 things, one of which, Bernardo already asked, which is what happens, you might have an exponential number of constraints. Actually, he asked this in the sort of MST context, which was important, but you might have a large number of scenarios. So then you try to use the ellipsoid method. And there are these sort of very nice techniques, which, if you haven't seen, it's a real treat to understand how to solve these exponentially large LPs. Okay. And there was an approach which was given by Schmois and Swami, which is sort of kind of nice and specialized to stochastic optimization. But let me give you a somewhat general theorem that will be useful out here. It's okay. So we said, the explicit scenarios, what if there are n scenarios given up front? How can we solve this? Well, how we can solve this is we just, maybe relax and round, right? But what happens if you had just a black box or something? So one natural thing is sample a whole bunch of times from this black box. You get a bunch of scenarios. Every time you sample, you get a scenario. Solve the problem on these scenarios. Okay. And so hopefully, just somehow sort of law of large numbers or something should say that if you sample enough times from this black box and solve the problem, it should be pretty much like the ocean problem. So the question is, what is large?
One question. So if you do this sample average approximation,
absolutely.
Our goal is to approximate the objective function that showed, for instance, in the 2-stage program. So are you trying to approximate the histogram? Or?
Good. So let me answer this question using the next slide. So that's exactly the right question to ask, and Cristobal is already on the ball. See, what we want is, this is the objective function we want to solve. It's some compact objective function where we are saying, look, I'm going to choose on the first day some x, and then choose some possible outcome. Now, omega is the same as K previously of the cost on the second day. Okay. Now, what you could say is, and say, capital X is the set of all first stage decisions. I'm being very general out here in some sense. So I'm saying, look, you can make a first stage decision, and then this is the second day cost. Okay, maybe, yeah. So it even gives you the thing nicely animated. And what I'm saying is you can sample n times and look at the sample average, the empirical problem. And the question that Cristobal is asking is, well, are you trying to say that f and f prime are very close to each other? Or are you saying something else? Now, clearly, if f and f prime are very close to each other, then you will make the same decisions. But that's too rigid a requirement. Because there are things that happen here with exponentially small probability, but which might have a very large cost. So if you keep, if you want f and f prime to be close to each other, you might have to get a lot of samples. So let me just give you a very simple example. Here is situation 1. Nothing needs to be covered on day 2. The second stage is 0. And the other situation is with some tiny probability, a single set needs to be covered on day 2. So if you wanted f and f prime to be close to each other, you better get this scenario. And that's too expensive sometimes. The probability, rare events might happen. So you got to be careful about that. But what you can take advantage of in these problems is you can say, look, if the costs do not change by too much, then you only need to figure out whether you need to buy things on day 1 or on day 2. You don't really care if f and f prime are the same. Put differently, what you care about is that f, let's say the arg min of f prime, if I call this x hat, then I want to say f of x hat is close to f of x star. This is the optimizer. Say x star is arg min of f. This is what I really want, right? And in fact, you can achieve this. So the statement I want to make is under some conditions, and maybe I'll mention one specific set of conditions which I find particularly appealing. The nice, clean conditions. So they say, suppose I have this two-stage optimization problem, which has the following properties. The costs are non-negative. Okay? And that there is an action which is like do nothing. I think of it as do nothing. It's a default action, which has, let's say, cost 0. And all these conditions can be relaxed a little, but it's just such that every other action differs only by lambda times the cost of this action in the first stage. Okay. So I say, look, if you screwed up, if you did action X instead of action Y, so this says the g of x omega minus g of y omega is at most lambda times the cost of x plus the cost of y. Because the distance of both this and this from this default action is at most lambda times the cost. So in some sense, this is like a Lipschitz-Ness property. It says like two actions can't differ by too much cost. Okay. So in particular, all these conditions are satisfied if costs go up only by like lambda. So if you do this, then here is a sort of theorem that I can say. Sample how many times? Sample some number of times. So you'll sample things which depend on, this is, X is the number of actions, remember, on day one. So let's think of this like a vertex cover. This is like 2 to the n is the number of actions. So log of 2 to the n is n. Okay, that's not terrible. Lambda, the inflation parameter, and 1 over epsilon times. So you just sample so many times and construct this function f prime. Look at its optimizer. It is close in behavior to the optimizer of the original function with very high probability. So you can use this to now, just reduce to the finite scenario case.
Oh, just a quick question. So
Please.
in this case, we're not considering that we can do something on the second day. You said like X is only the actions on the first day.
Good. So you're absolutely right. So what's happening is I've bundled all that into this expression gx omega, which you should think of as the best cost. Oh, sorry. So let me say it instead of writing it. It's the cost of the best recourse action on day 2 if X on day 1, if we did X on day 1, and omega is the scenario. So I've kind of bundled it all into this thing. It's easier, it's compact representation.
Perfect, thanks.
Absolutely. That's a very good point. Okay. And observe, it does not compare the values of f and f prime on an x by x basis, only on the minimizers. That's what you care about. Okay. By the way, how do you prove such a result? You prove it using a concentration bound, really. But you concentrate. I can give you I can flash the intuition for the proof. There are dangerous scenarios, and there are nice scenarios. On nice scenarios, you have concentration, and there are very few dangerous scenarios. And that's, maybe I'll refer you to the paper for the actual proof. It's not a difficult proof. It's just, given this outline, chances are you can start working towards this proof yourself. And it's a very natural idea. Like you have high variance. This variance could be caused because of 2 reasons. Good. Okay. So, and by the way, the way I presented it, I presented it for a finite set of actions. So this had log of x in the theorem statement. The full theorem also holds for linear programs, of course. So you can use it for stochastic linear programming as well. And do you need so many samples? So each of these terms, really, you do need them. But on a like problem by problem basis, you might not need them. There are some problems on which you do, some problems on which you don't. Okay, so maybe at this point it's a good idea for me to sort of look at the time and say skip over. There is a discussion of a problem called two-stage Steiner tree. I'll have to define the problem and then talk about it. You can have a look at it offline and send me a mail if something seems worrisome, or if you want more details, or if you just want to chat about this. But let me just skip over this thing. Basically, the point of this whole picture was, of this example was, in some cases, your sample complexity can be reduced a lot. And this is something that I haven't really talked about too much. If I give you black box access to the distribution, how many samples do you need in order to get a good approximation? This is a big deal. The sample complexity is, it's like money, right? Okay. So let me okay. Two closing thoughts. One is a lot of this can be extended to case stages of decision making. You don't just have one stage, but 2 stages, but case stages. And we'll discuss more about that in the next. Some of these techniques extend. So you can write down massive LPs and you can solve them using ellipsoid. But in some other cases, we make assumptions like independence to make our life easier, and which will really be the focus of the next talk that I'll give. And just looking forward, if you want to sort of think about something for the next talk. So here is the problem that I'll tell you. I'll give you n boxes. Each box has a price, but the price is a random variable. Okay. What you can do is you can choose a box and open it and see the random variable inside it, the actual value of the random variable. So once you open the box, you see the actual value. Now you have to decide whether you should take this or you should move on to the next one. If you move on to the next one, you can never come back. Okay, so it's like going to a shop and looking at the, you know the prices, some distribution on the prices, you don't know the actual price, but you see the price. If you leave, the salesman is never going to sell it to you again for whatever reason. What's a good strategy? Okay. And so what happens is if you think of this as a multi-stage problem, this is a very complicated problem. The number of scenarios is exponential, both in the outcomes and in the number of stages. But it's a product distribution. Let's say things are independent. The prices and the first variable is independent, the second variable, and so on. So these are the kind of questions that we'll move to next. And we'll see again the power and limitations of linear programming based approaches. Okay, so let me stop here and take any more questions that you guys have. And of course, it's lunchtime for you guys. So.
Yeah, I don't see any questions in the chat right now, but now there's one. Do you see it, or do you want me to?
Yeah. No, so Arthur was asking, sampling problems very different if the sampling has a cost on the objective function. Yeah, good. So if sampling introduces a cost, if the sampling complexity is the, so I don't know offhand, Arthur. It's I don't know of results which are trying to optimize the sample complexity beyond the ones that I mentioned. There are similar results, but they usually say just poly time. So they're polynomial in the number of in the parameters, in log of x and lambda and things like this. So, and Karthik says, is the last setting you mentioned related to profit? It is related to profit inequality problems as well. And so we'll make those connections more precise next time, for sure. Absolutely, Bernardo. We model uncertainty on the number of stages. So for instance, here is something, so one natural way of doing this is to view this as like a Markov chain process or Markov decision process. You could say, look, I am going to, here is the graph. At each point in time, the next request is going to be from another vertex of the graph, but there is some probability that I stop. So a Markov decision process or a Markov chain in this case would be a very natural way of modeling it. The results known for these are few and far between. It's a very interesting area, and I think if you're interested, this is a great direction to look in. So put very simply, I can even just say at every point in time with some probability P, I flip, at every point in time, I flip a coin with bias P. If it comes up heads, I stop. If it comes up tails, I keep on going. That's a very natural way of modeling uncertainty.
Maybe I'll stop the questions for the time being.
Okay.